Coming to the topic of discussion, electron spin resonance spectroscopy. This topic, the fundamentals of this topic is not very strange and new to you, because there is a synonym, there is a parallel to this in terms of its principle, in terms of nuclear spin resonance spectroscopy, which we call NMR, nuclear magnetic resonance spin spectroscopy. And in your last semester as well as this semester, you have been learning a lot of things in NMR. Except in NMR, the spin of the nucleus is the focus of discussion, whereas in ESR, it's the spin of the electron which is the focus of the discussion. And all the things we do is based on some parameters of the spin of the electron. Now let us look at some basic properties of electrons which are relevant for our discussions in future. The mass of the electron is so much, the electron charge is so much. The negative sign on the electron charge suggests that electron is a negatively charged particle. The spin angular momentum, characterized by the quantum number S, is quantized again, is given by h divided by 4 pi or h cross h cut divided by 2. Please remember that h cut, wherever we refer, means h divided by 2 pi. It also has magnetic dipole moment, which we are going to discuss later, which is given by the expression GE mu E S. Now, as we know, in any spectroscopy, to get a line, to get a band, or to get a peak in the spectrum, every line in a spectrum corresponds to a transition between the energy levels. So even in ESR, we are looking at transitions between two energy levels. Now let us discuss how these two energy levels are formed and which are those two energy levels we are looking at. Now let us consider a very simple system of a free electron. Now what do we mean by a free electron here? An electron which is not under the influence of any other potential energy, like the attraction by the nucleus, or for example repulsion by some other electrons around. We have a single electron which is free, in the sense a single electron which is isolated. Now as we know, a spinning electron will have, in atoms example, we will have two types of angular momentum, the orbital angular momentum and the spin angular momentum. The orbital angular momentum, we can conveniently keep it out of the discussion when we speak of ESR. Why? Because the orbital angular momentum, we say, is quenched. What do you mean by this? The orbital angular momentum would have already formed a fixed orientations which cannot be further altered because of the influence of the electric field internal in the molecules. Please remember, the orbital angular momentum in the molecules we are telling as quenched, not in atoms, in the molecules. And chemistry, we always look into the structure of molecules. So in molecules, the orbital angular momentum is said to be quenched. There are bonds which contain electrons, and these bonds are also directional. The chemical bonds, the covalent bond is directional. Therefore, according to the orientations specified by the directions of a pre-existing bond, the orbital angular momentum would have had fixed orientation which cannot be altered, which cannot be further tuned by the application of an external magnetic field or an external electric field. So orbital angular momentum doesn't come to our help too much in ESR. Now let us consider about the spin angular momentum. We all know a spinning particle, be it a nucleus or an electron, has a spin angular momentum which is intrinsic to a spinning body. Now this spin angular momentum is represented, by the quantum number S, which can have, in the case we are considering an isolated free electron, S is equal to half. Only one value is possible, S is equal to half. Now we will now later understand the influence of the electric field on the spin angular momentum of this electron. But before this, we will look into one thing. Is ESR spectrum universal? I mean, can any molecule give an ESR spectrum? That's the question. The answer is no. When compared to NMR, the ESR is not an universal technique in the sense most of the molecules are ESR inactive, but most of the molecules are NMR active, because we are looking at the spin. Usually in the proton NMR, we are looking at the spin of the nucleus of the hydrogen atom bonded in the molecules. And we all see that if we consider organic compounds, almost all organic compounds will have at least few minimum hydrogens. Therefore, all molecules become NMR active. But when we come to spin electron, when we come to ESR, all molecules are not ESR active. Why? Because to be ESR active, it should satisfy a prerequisite condition. What is that prerequisite condition? It should have at least one unpaired electron. Why? Because we all know for the paired electrons, the spin get cancelled. Example, let us consider electron in a 2s orbital, or okay, even in a molecule, let us consider electrons in sigma orbitals, pi orbitals. In sigma orbitals, if there are 2 electrons, one electron will have s is equal to half, the other electron will have s is equal to minus half. Both electrons cannot have s is equal to plus half or s is equal to minus half. Therefore, plus half and minus half cancel out. They become paired up, and therefore they spin cancel and become ESR inactive. Now, maybe that you can guess what type of molecules would be ESR active. In the atomic or in the molecular orbitals, at least one orbital should contain one unpaired electron or odd number of electrons. So, what are the type of species which give this odd number of electrons or the unpaired electrons? I don't think only of the molecules. You can think of any chemical species. It can be reaction intermediates also, like ions and free radicals. Of course, the guess is correct, the free radicals, because the free radicals are formed by homolytic bond cleavage, and the radical species will have odd number of electrons. Free radicals are ESR active. There are molecules even which themselves contain odd number of electrons. Example, NO, NO2, ClO2 like this. And please remember, most of the times such molecules you cannot represent their structure using Lewis structures. Such molecules are odd electron molecules. There are even electron molecules like oxygen, but the oxygen is in its triplet state. So molecules which are excited to their triplet states are also ESR active. And there are a lot of D block metals which in their complexes contain unpaired electrons, paramagnetic complexes. They are also ESR active. F block metals, many are ESR active. There are also impurities. So what is the summary? Although the ESR is not as universal as NMR, but at least it is specific to characterize some important species in chemistry, like free radicals, like molecules in their triplet states. Please remember, ESR is a very powerful tool to identify the excited molecules when they absorb light, which maybe you will cover it in your UV spectroscopy or, for example, photochemistry. Now let us move on to the fundamental equations governing the ESR. As we know that spin angular momentum, which is identified or which is characterized by the quantum number s, is quantized and is given by s is equal to square root of s into s plus 1 by s into s into h divided by 2 pi, where s is equal to half. Like the system we are considering a single isolated system, s is equal to half, single isolated electron, s is equal to half into half. So if you substitute all those things, you will get square root of 3 divided by 2 into h. Now that's fine. But we all know that the spin angular momentum is a vector whose length, whose magnitude is given by the equation s is equal to square root of 3 divided by 2 into h divided by 2 pi. But what about the direction of this vector? If you rewind your brains a bit back into the quantum mechanics chapters, you see that when there is no external field or when there is no magnetic field, the direction of this vector can be in any direction. In the sense, if you consider a sphere and this vector's arrow can point to any point in the sphere, we call that free tumbling in space. However, what happens when a magnetic field, external, or an electric field is applied? This is a classical experiment of Zeeman effect, in fact, is it not? If you record even atomic spectra under the influence of electric field, you will get more lights, splitting of the lights. What happens? Inherently, the direction of this vector, which vector? The spin angular momentum vector, gets fixed to specific orientations in space. Now, the question we next up, how many orientations are possible? The number of orientations possible is governed by the value of the S. If S is equal to half, there are only 2 orientations possible. And that orientations, directions of the magnetic field in the Z direction, or that orientations of the vector, we always measure, quantify in terms of the direction, relative orientation with respect to the applied field. Now, if the applied field is on the Z direction of your Cartesian coordinate system, it can be in any axis, but Z we take conventionally. It's a convention that we take Z axis. With respect to the external applied field on the Z axis, what are the orientations of this vector of the spin angular momentum? We see if S is equal to half, 2 directions are allowed, and we come to a new quantum number, that is MS, magnetic spin quantum number. So what is MS? MS is a quantum number which comes to picture only in the magnetic field application scenario, external magnetic field application scenario. Fine. Now, if S is equal to 1, what are the orientations possible? MS is equal to -1, 0, +1. If S is equal to 3 by 2, -3 by 2, -half, 0, +half, +3 by 2. I hope you know how to arrive at these directions by applying the rule S +1, S +1 -1, S +1 -1 -1 till you go on to get S -1. Now, for the electron we are considering for our discussion, it's a free electron. S is equal to only half. Therefore, only 2 orientations are possible, which are characterized by MS is equal to +half and -half. Fine. Now, remember, still we have not separated, we have not got any 2 energy levels, basically, which are required, prerequisite for a transition. Now, when we have orientation, which is given by +half and -half, let us see, can these +half and -half orientations differ in energy, or are they degenerate? This is a very important question which we are going to address now. Are these +half and -half orientations degenerate, or they are of different energy? Now, let us arrive at an equation for the energy of these spin states. What are the spin states? I mean, the spin state which is characterized by +half, the other which is characterized by -half. A spinning charge creates a magnetic moment. Magnetic moment is a naturally created moment by any spinning charge, be it be an electron or be it be a nucleus. What is the expression for the magnetic moment of the spinning electron, which is given by mu e? Mu e is equal to GeE divided by 2m into the magnitude of the vector, which is given by S. Now please do not confuse this magnetic moment with momentum. Okay, momentum is basically your mass into velocity term basically, but moment M-O-M-E-N-T, moment is a force. So now we are looking into the force, magnetic moment created by the spinning electron, which is given by that expression mu E is equal to GeE divided by 2m into S. We all know S equation, which is square root of 3 by 2 h. We can substitute there and get the expression for the mu E, which is the magnetic moment. This slide of course explains how you get the mu E, which is the magnetic moment. What is GE? GE is a dimensionless constant, which is called the electron G factor, and its value for a free electron is 2.00232. In fact, the catch is here. The value for a free electron, G value for free electron, it also means there are differing values of G for electrons in different environment. Now a free electron which is isolated, which is not under the influence of any field, the G value is 2.00232. E is the electron charge, M is the mass, and these are the constants. You can combine E h cut divided by 2m into a bigger constant and represent it by beta E, which is called Bohr magneton. Please remember, Bohr magneton is a constant. Now we come to something interesting. Like the spin angular momentum of an electron is orientation is given by the Z, like, okay, let me repeat it again. Like the spin angular momentum has S as well as MS values. What do MS tell? The orientation of the spin with respect to the magnetic field. This is called Z component of the angular momentum. So what is Z component of the angular momentum? MS value. MS is the Z component of the angular momentum. Now we have magnetic moment. This magnetic moment will also have its Z component. Which is called, or which is described by the interaction of the magnetic moment mu Z with the applied field of strength Bz. If the applied field is B, why is that Z? Because we are considering the applied field in the Z direction only, not on the X and Y axis. You can consider that, but anyways, it doesn't matter. Z axis, we have chosen it arbitrarily. Z axis is interacting with the magnetic moment, which is created by the spinning electron. Now, what is this magnetic moment value in different directions which have already been fixed? For example, plus half direction and the minus half direction. The energy of that interaction, which interaction are we speaking of? The interaction between the applied electric magnetic field Bz and the magnetic moment created by the electron, spinning electron. But since as soon as we apply an external magnetic field, the angular momentum vector gets aligned in two different directions, we will look into the interactions only in these two directions. Therefore, the energy of that interaction is given by minus mu Z into Pz. What is mu Z? It is nothing but GE beta E into MS. Maybe we can go back to the previous slide where mu E is the magnetic moment of the electron, which is given by GE beta E square root of S into S plus 1. What is the mu Z? How is it different than mu E? Mu Z is the interaction of the magnetic moment with the applied field Bz. Since the angular magnetic moment, or since the spin of the electron, angular momentum of the electron is quantized with respect to the external electric field. Now the energy we are looking with respect to only those two specific directions. Therefore, we are using the quantum number ms. Okay, if you look at this formula, square root of s is half. It doesn't speak anything about the orientation of the electron. That mu e is the magnetic momentum created by the electron when there is no external field. 11.1 equation is the magnetic moment created by an electron when there is no external field. But when there is external field, the magnetic moment in the z direction is important to us now, which is given by GE beta E into ms. The energy of the interaction between the magnetic momentum and magnetic moment and the applied field is given by E is equal to GE beta E ms into bz. Now, what are the values possible for ms? As we know, for a s is equal to half system, which we are considering, plus half and minus half are possible. If you substitute those two values in the equation 11.2, you get two different energies. One plus half GE beta E bz, the other minus half GE beta E bz. So, we have now two energies for the same electron which are different in their quantities, which are different. Look at this diagram. The energy levels have got separated, or the energy levels have been formed because of the application of external magnetic field. If you lift the external magnetic field, if you release the external magnetic field, what happens? B becomes 0 and the spin states become degenerate. If you have external magnetic field, the spin state become non-degenerate or of different energies. We can also quantify those energies. E is equal to plus or minus half GE beta E into Bz. Please remember that we can designate these states by alpha and beta symbols. Beta state is the one which has ms is equal to minus half. Alpha state plus half. And why has beta state decreased in energy whereas alpha state increased in energy? The higher energy state is denoted by alpha, which is aligned parallel to the magnetic field, applied magnetic field, whereas the beta state has aligned anti-parallel to the external magnetic field. In fact, when you are looking at the non-degenerate alpha and beta state created by the application of external magnetic field of the nucleus, you write the same diagram, except the alpha state is the lower energy state, whereas beta state is the high energy state. So now it is reversed here, in fact, but that doesn't matter for the, because after all in all spectroscopy you are looking at delta E basically. So that doesn't matter. Anyways, convention wise it matters. The beta state is the lower energy state, the alpha state is the higher energy state. Now what is the delta E value of this? You have to subtract the energies of alpha and beta state and you get delta E is equal to GE beta E into Bz. G is the G value of the electron. Bohr magneton Be another constant. Bz is the applied magnetic field, strength of the applied magnetic field. Now please go back to this. Let us go back to this diagram and see that. the delta E value is not absolute. It is relative to the field strength. If you increase the field strength, the separation between the energy levels increase. Therefore, when you satisfy a resonance condition, what do you mean by resonance condition? Resonance condition in spectroscopy always means the difference in energy delta E between initial and final state is equal to the energy of the absorbed radiation. This we can also, the energy of the absorbed radiation can be expressed in terms of frequency because E is equal to h mu. They are interconvertible. Therefore, h mu is equal to GE beta E into Bz. When is the resonance condition satisfied? When the mu of the incoming radiation or the absorbed radiation is equal to delta E. But since delta E itself is relative to the field strength, you can have resonance conditions satisfied for different values of Bz. So you can have a range of Bz, and for every Bz value there is a corresponding mu value. What is mu? Is the frequency of the applied radiation or the absorbed radiation. Mu. So we come to a point now. How to characterize the absorbed radiation's frequency? That is very important in spectroscopy. Is it not? The absorbed radiation's frequency is very important. That is what is the characteristic of the spectrum, which is in turn important for characterizing the compounds. Usually for free electron, if we are speaking of, as of in this example, the practice is you can apply a magnetic field at two different values, 0.34 Tesla and 1.25 Tesla. If you do that, what is the corresponding frequency of corresponding value of mu? For 0.34 Tesla, the value of mu is 9.5 into 10 to the power of 9 Hertz, whereas for 1.25 Tesla, it is 35 into 10 to the power of 9 Hertz. Please remember, 10 to the power of 9 Hertz is called gigahertz. So 9.5 gigahertz or 35 gigahertz. Where does this mu fall in? Another important question. In NMR, the absorbed radiation's frequency falls in radio waves region, whereas in ESR, the absorbed radiation's frequency falls in microwave region. The 9.5 gigahertz lies in the X band of microwave region, whereas 35 gigahertz lies in the Q band of microwave region. Now, why does this happen basically? Why the radio waves is absorbed in nuclear magnetic resonance, whereas microwaves are absorbed in electron spin resonance? Because of delta E's difference. If you look at this diagram, for an NMR, even with respect to the applied field, the delta E is small. For the same strength of the applied field, you look at the ESRs or the electron spin states energy difference is too much. Smaller energy means smaller frequency of radiation is absorbed, that is radio waves are absorbed. Larger energy means higher frequency of radiation is absorbed, that corresponds to the ESR, that corresponds to the microwave of the region. So basically now we are like in NMR, we come to a condition here. As I told you, the delta E is not absolute, it is relative to Bz. You can record the spectrum either by keeping the Bz constant and go on sweeping the microwave region and see where the absorption occurs, or you can keep the frequency of the incoming radiation or the applied radiation same, identical, and keep sweeping the field and see where the resonance happens or where the absorption happens. In practice, both in NMR and ESR, the frequency is kept constant and the magnetic field is swept or the magnetic field is varied to find the resonance conditions wherever the absorptions happen. So, if a spectrometer in ESR is operating at a frequency of 9.5 gigahertz, it is called an X-band spectrometer. If it is operating at a 35 gigahertz, it is called a Q-band spectrometer. This frequency, operation frequency is also fixed for many NMR instruments. An instrument can operate at 400 megahertz, 600 megahertz or 200 megahertz, like that. Similarly here. And please remember, even in NMR, we have a chemical shift value also here in ESR. Anyway, that we will come to the point later. Now let us see how an ESR spectrum is presented. Like we know, any spectrum contains an x-axis variable, which is usually in all other type of spectroscopies is the frequency or the wavelength of radiation, but in NMR it is the field strength. ESR also the x-axis is field strength. What is Y? Y is the absorbance, which shows how much of radiation is absorbed at that frequencies. The difference in the presentation of the spectrum of the ESR is the spectrum is not presented in its direct XY relation curves, rather in the first derivative of the absorption curve. So why do we do this? Because the absorptions are very broad in ESR. So we cannot pinpoint the absorption maximum absorption specific value when we have very broad peaks. But the same peaks, if we convert that into a derivative, first derivative, we get first derivative spectrum whose center point in fact gives you the absorption maximum. But the conversion of a curve into its first derivative is not a very big task, which you have already done. Of course, not in this context, in your practicals. If you remember how you do the potentiometric titrations, the first curve of a potentiometric titration would be simply EMF versus the volume of potassium dichromate added. The second curve is what? Delta EMF divided by delta volume. Same thing here. Delta absorbance divided by delta BZ value, and you plot those delta values, you get the first derivative curve. And this we have discussed. It simply shows the difference for the same applied field, delta E separation of ESR and NMR. A very block diagrammatic representation or block diagram representation of the ESR spectrometer. Basically, what should you have? You should have a source which generates your microwaves. That's a klystron source, and you should have a sample chamber where the sample is placed, and sample is placed, of course, in between the poles of a magnet. Basically, these are all superconducting magnets whose field is varied by the variation of the applied voltage, and you have a detector which detects the raise or the fall in the intensity of course it cannot raise in intensity, the fall in intensity of the microwave region whenever the absorption takes place. And all this data is fed into a computer which displays you the curve, ESR curve. Now, what is the point? This is the whole point, that you have two energy levels represented by beta and alpha states, and the delta E between the energy levels is given by GE beta E into BZ. With this fundamental equations of resonance or the delta E equation, only with this equation, in fact, you can solve simple problems like this. A specimen of zinc oxide shows a strong ESR line at a frequency 9.45 GHz. Calculate the G value of the line. So what are the things you require? When we are given a problem where they are telling it is 9.45 GHz, then the corresponding BZ value, the applied field value, would be, because that's the X band, would be 0.34 Tesla. So substitute 0.34 Tesla for BZ. Beta E is a constant Bohr magneton. You just require the electron charge and the mass, which of course you can refer to the first table I give those values. GE is a very important point. What is the GE value we should take? Like I told, the GE value differs by the environment of the electron. But now the specimen of the zinc oxide, the electron is not under the influence of any magnetically active nucleus. So you all know that all those nucleus with I is equal to 0 value doesn't give you an NMR spectrum. Zinc and oxygen both have I is equal to 0, or the isotopes of this zinc and oxygen in this problem both have I is equal to 0. Therefore, the electron is not under the influence of a nucleus which is magnetically active. When the electron comes under the influence of a nucleus with I is equal to non-zero value, then it is no longer a free electron. So the GE value differs basically. Anyway, since all our discussion has concentrated on a free electron, the GE value you can take as the same GE value for a free electron, which is 2.00232 and solve such problems. Fine. So I hope that I have put across to you the basic resonance equation, that is the delta E equation, which is fundamental for any type of spectroscopy, the delta E equation for a free electron. Now, as we know that if you get a single line always in any type of spectrum, it is not a useful spectrum. We should get more lines, or we should get variations in the frequencies of the lines depending on the structure of the molecules. So by studying the lines and their variations, the number of lines, we can interpret the structure of molecules. For this to happen, we should move on to systems which are not equivalent or not similar to a free electron system. So what are the systems we can think of? The system is electron, which is in chemistry, what is the system we can think of? Or in molecules, what is the system we can think of? An electron which is under the influence of a magnetically active nucleus. That is a nucleus whose I is equal to non-zero. I can be half, I can be 3/2, I can be 1. If we consider such systems, then we will see that a single line in this ESR spectrum, which is for a free electron, and that single line is always of fixed Bz value or fixed mu value, gets splits into many lines. Also, the frequency of absorption or the position of the line in the spectrum also gets shifted. So we are going to study such systems in our next presentation. Start by a simple hydrogen atom where there is single electron, of course, which is under the influence of the nucleus. I is equal to half. So let us see what happens to the ESR spectrum of a hydrogen atom. Now, today we have learned the ESR spectrum of a free electron. Of course, we cannot call it a spectrum because already we know its value of delta E. You need not even do an experiment. Theoretically, you can find out what is the delta E value, corresponding frequency, or for the applied field you can find out. But anyways, this is a very fundamental equation, the delta E equation, which forms the basis for a bit advanced discussions in the next presentations. I hope you have found this useful. Please give your comments, feedback. You can message me, you can ask me questions, and then we can move on to our next presentations. Thank you and have a nice day. Thank you.